All right, so our next speaker today is Ratul Mahanta from University of Winnipeg, and he will be talking about dimensional reduction of geometric moduli in GKP compactifications. Ratul, you have 25 minutes. Please go ahead.
Okay. So first of all, I'd like to thank the organizers for giving me this opportunity to present our work. So this is based on this work, which is written with Andrew. And I would like to start by giving some introduction and motivation of the work. So in the 10D type 2B supergravity in presence of D branes and O planes admits GKP backgrounds. This background feature a 10D space-time, which is a warped 4D Minkowski space-time, and a 6D conformally Calabi-Yau orientifold. So this is the conformal factor, and the leftover piece is Ricci flat internal manifold, and A would be the warp factor. We'll talk about the Weil factor later. So the three-form fluxes shows this warp factor through a Poisson equation. Since the three-form fluxes are quantized in units of alpha prime, therefore the warp factor goes as alpha prime squared. In the large volume limit, the effective action from a direct product compactification, which is Minkowski times Calabi-Yau, is a good approximation, and therefore the warp factor and flux corrections are order alpha prime square. Okay, so a GKP background can be deformed by a set of parameters yielding a family of 10D solutions. Upon compactification, they lead to massless fields in 4D. So we aim to compute the moduli space metric even in the case of strong warping. For the present work, our focus would be the geometric moduli, which are the deformations of the internal Calabi-Yau manifold. And these will include all the Kähler deformations, along with certain complex structure deformations, which we will refer as flat complex structure deformations of the internal Calabi-Yau. These moduli have not been dimensionally reduced previously. I should give a status of what has been done earlier. So earlier dimensional reductions focused on the universal volume modulus, actions descending from the form fields, D3 band position moduli, but the geometric moduli has not been dimensionally reduced. However, in a different approach, the Kähler potential for the geometric Kähler moduli has been derived from a combined consideration of the expected n equals to 1 sushi properties of the 4D effective theory and the structure of 10D vacua. So when we dimensionally reduce the geometric moduli, especially the Kähler deformations, we can compare with these results. But the moduli space metric for the complex structure flat deformation should be for the first time in the literature. Our method, which is the dimensional reduction methods, rely only on the 10D equations of motion. Therefore, they apply whether the GKP background breaks sushi or not. And this is an advantage over this method. So this can also be applied in more general compactifications like non-Calabi-Yau compactifications also, but we'll for time being restrict us to the Calabi-Yau compactifications, warped Calabi-Yau compactifications. Okay, so this is the outline for the remaining talk. And I should start with the second part, which is the geometric moduli space in GKP compactifications. Here I have given the GKP background. You can see the metric is a warp product spacetime. I have also given the 5-form field strength and also given the condition on the 3-form flux. The Weil factor is written here, which can be adjusted so that upon compactification, the 4D Einstein-Hilbert term is canonically normalized. So I should also say that there is more general, okay, so this is the orientable limit of the F theory, where the tau is constant, but there is more general backgrounds, GKP backgrounds with varying tau, especially on the internal manifold, and also non-Calabi-Yau extra dimension, but we will restrict ourselves for this kind of backgrounds written here. F tilde phi as given is self-dual in 10D. To match the low energy limit of type 2B superstring theory. So it's a constraint coming from string theory, as well as also to ensure the closure of 10D Sushi algebra. Importantly, the background three-form flux features components only on the compact directions. This is a harmonic form, and it is imaginary self-dual with respect to the background orientable. So this is this will be an important condition for us. I will soon explain in more detail. We'll consider linear fluctuations around the background Calabi-Yau metric. For time being, take U as a constant parameter. So we are, I should mention that the knot has been used here to denote a background, and we are fluctuating away from the backgrounds through a constant parameter U. But we are ensuring Ricci flatness at linear order, and also preserving the unwarped volume at linear order. This is because we want to deal with the non-volume geometric modulus. The volume modulus has already been dimensionally reduced earlier. Okay, so in response, like since we are fluctuating the extra dimension internal manifold, in response, we need to allow fluctuations in the warp factor, the Weil factor, the axiodilaton, the three-form flux, and also the field strength, five-form field strength. It is because if we depart away from the background and we want to still satisfy the 10D equations of motions, we need to adjust the background. So we have fluctuated them. We want the deformed 10D system to remain a solution of GKP type. So it is really we are going from one GKP solution to another GKP solution. So there is a family of solution we are expecting. The part of three-form flux must be ISD at linear order because it should be a solution of GKP type. So this is an important relation for us. I will refer it as linearized ISD. In one hand, it has a form 3 from W3, which is the response of the fluctuation of the metric on the background 3 from flux. It is coming when you linearize the star operator for a background. And on the other hand, on the right hand side, it has the eta 2 potentials, which is used to shift the G3 flux and also the shift in the axiodilaton. So I will discuss this in some detail now. So before that, I want to say that the fluctuations are found in order to solve the linearized 10D supergravity equations. I am not giving details here. For the Kähler deformation, the metric fluctuation is given by a harmonic 1-1 form. For the complex structure deformation, they are given by harmonic 2-1 and 1-2 forms. For any Kähler deformations, we have deduced that delta tau vanishes and the linearized ISD condition can be satisfied. It can be found in the paper. However, depending on the background flux and the complex structure deformation, the linearized ISD condition can be satisfied if the harmonic piece in the W3 cancels the delta tau piece on the RHS. Axiodilaton remains flat because the delta tau piece should be non-zero. So I should say that this equation on the right hand side has a Hodge decomposition structure. This term is exact. This can be written as a co-exact form, and this is harmonic because the background flux is harmonic in the GKP background. So any harmonic piece in the W3 should match with this component on the right hand side, and if this can be done, then we will call the complex structure deformation in that background is a flat direction. Complex structure deformations, those violate these linearized ISD conditions, are stabilized and they are beyond the scope of the current work. We will focus on the flat complex structure deformations. I should also mention some non-geometric moduli of GKP compactifications. One can vary the C4 form in this fashion. BI would lead to some axionic fields. And I am stating here because it has been dimensionally reduced earlier, but we will combine this with our results at the end. So now the third part of the talk, the dimensional reduction and 4D moduli space metric. Consider the metric fluctuation where you allow the space-time dependence on the parameter now. And the y-dependent part is either a Kähler deformation or a flat complex structure deformation. We first need to find the correct 10D fluctuations. Second, we need to substitute those into the 10D action and integrate y. So I should explain in a moment that what do I mean by correct 10D fluctuations. I have written here our answers. You can see here that since u is now space-time dependent, derivatives of u appears. These are the new terms. And also there is a compensator field as a off-diagonal term in the metric ansatz. Expanding u and its derivatives, the 0th order terms coincide with the GKP background. And at linear order, the self-duality of f tilde 5 has been maintained. If you further set u as constant, like set the x dependent to go away, you will, these are the fluctuations that I have shown in the previous section. So there are some new terms. And that is required to solve the 10D linearized equation of motions. So satisfying 10D Einstein field equations of motion for the form fields and Bianchi identities at linear order, we get equations of following types. The fourth equation will be satisfied only on on-cell. So this will not be of our concern. Basically, once we deduce the 4D action, we want this equation as a Euler-Lagrange equation of motion coming from that equation. But to derive the 4D equation, we will not impose them. But the first three are important. Among them, the first ones, any terms proportional to u, we set it to 0. And this has been done in the previous section. And the deformed 10D system remain on the moduli space of GKP compactification. So this is because we want to stay on the moduli space of GKP compactifications. Then new equations are the these parts and these parts which comes with the derivatives to vanish. Satisfying these equations leads to constraints on the fluctuations. We'll impose them on cell to derive the to deal with the action. And they are important for the 10D gauge and diffeomorphism invariance. So these fluctuations are not arbitrary functions. They satisfy certain Poisson's equations. And that is what I mean by the correct 10D fluctuations. And the y-dependent parts satisfy certain equation. And that's also good because we need to know their functional forms to integrate the y. Because if we do not know what are they, we cannot integrate over y. So the Poisson equations for the fluctuation in the warp factor and the compensator field in the metric are solved respectively in terms of biscalar and bivector Green's functions. Using a relation between derivatives of these Green's functions,
That's
we can
nice.
satisfy.
I signed up.
Sorry.
Is there a question? No.
Okay. So using relation between the derivatives of the Green's function, we can satisfy another constant that we get, which relates the divergence E to divergence B to the variation in the warp factor. So everything is in place. We know this explicitly. And now we will be working with the action to get the 4D action. To work with the action, there is an organizing principle. Schematically, one can consider action for some set of fields psi A. And they have the equations of motion. And one can consider a background and take fluctuation around the background values. This would generate some linear fluctuation in the equation of motion operators. So this would involve the fluctuations in the fields and their derivatives, so they are linear. And now if we plug this fluctuation in the action at 0th order, we get a constant. At linear order, terms vanish by the background equation of motion. At second order, we get this expression. You can see that this is first order, this is also first. So this is really a second order expression. So this is the schematically I said. So for us, we already know these quantities because dealing with the linearized 10D equations of motions, we computed these fluctuations. We can plug them in above expressions and impose the constants and integrate y. So there is some subtlety regarding the C4 fluctuations. Because the solutions, the fluctuations are taken to be self-dual. So we have kept only the magnetic component so that the action does not vanish. And we have dealt with that. Okay, so here is the result. For the case of geometric Kähler moduli, including the volume modulus and C4 actions, I have given the dimensionally reduced action. You can see here that V0 is the volume of the background Calabi-Yau. Certain one forms appears there, but they satisfy some Poisson equations, which is sourced by these 5 forms, and this is product of 2 harmonic forms. And typically in a Calabi-Yau with a non-formal metric, they are like a product of harmonic forms are not harmonic, and therefore these are non-trivial contributions which can be solved in terms of some Green's functions. And recall that the metric fluctuations comes from a basis of harmonic one-on forms, which will also create some fluctuation in the Kähler form. And the action fields I have also given here, which are coming from the fluctuations of the C-force. And if you set the first form in the set as the Kähler form of the background itself, then U1 is the volume modulus. So volume modulus is also taken into account apart from the non-volume Kähler moduli. The moduli space metric depends on the background war factor, reform flux, axiodilaton, and implicitly on the background metric. So by this I mean to specify, to start with a background, we need to be somewhere in the moduli space of the Calabi-Yau. So if we vary these over the moduli space, these quantities will vary. So although this is a really a quadratic action, but you can one can find the nonlinear dependencies, the moduli space dependence by varying the starting point over the moduli space and compute it. So also which representative of the cohomology is harmonic depends on the metric. So they appear here. So there are many ways the moduli space matrix depends implicitly on the background metric. Okay, so in a similar way, we have obtained the 4D effective theory of flat complex structure moduli. There seems to have kinetic mixing of these form between the Kähler moduli and the flat complex structure moduli. We could not prove them to vanish, but however, these contributions drop in large volume limit. Okay, so now I will discuss some outlook. First of all, like one can develop computational tools capable of calculating the moduli space metric as the background COI metric is varied over the moduli space. This should allow for precision string phenomenology even in the case of strong warping. So this can be one future direction. And notably, there are recent advancements in numerically computing the metric on Calabi-Yaus and harmonic forms on them. So we hope that this can be in principle done numerically. And then the dimensional reduction of the massive complex structure moduli, like which violate the linearized ISD conditions. So that remains open for particular such moduli, which is a conical deformation modulus. First steps appears here, but some assumptions are there regarding the flux fields, but we believe that this needs shift violating the linearized ISD conditions. And also our F tilde 5 ansatz needs modification to deal with that. This is something we want to look in near future. There is the tadpole conjecture that suggests an upper bound on the number of stabilized complex structure moduli for compactifications on the Calabi-Yau identifolds with large Hodge number. These tests have been had been done using the 4D superpotential. For a given Calabi-Yau identifold and flux quanta satisfying D3 tadpole bound, determining which complex structure deformation satisfies the linearized ISD condition that I have shown poses a counting problem. We have demonstrated this in a simpler case of toroidal orientifold. Of course, these toroidal compactifications are not under the scope of this conjecture, but the counting problem has been demonstrated, and agreeing with previous results. So we have seen that our approach is equivalent to using the 4D superpotential, but offers an alternative formulation that may provide insight into proving the conjecture or finding counter examples, if any, by scanning over flux vacua. I want to say that stay tuned for a new version. This should arrive within a week. I hope so. This has some significant extension. This contains basically these explicit examples. And also we have tried to connect it, the linearized ISD condition with the F flatness condition of the 4D effective theory, although this puts some conditions on the Kähler potential, but this is, I would say, like we want to look further in the future. Thank you for your attention.
All right. Thank you, Ratul, for the very nice talk. Are there any questions?
So I have first, thank you for the nice talk. I think I communicated with Andrew and you a little bit about this issue, but I wanted to bring it up again because I think there's a problem with doing the case that breaks SUSY when you have a 3-0 component in your flux, because I don't think there's a solution. So if you don't have a solution, then what do you mean by the moduli space or any of these other issues? Because what you've neglected here are the ingredients that you need to actually have a compact solution. The orientable the couplings on orientable planes and the associated couplings on D-branes. And when you include them, you will get a potential energy in the case with the 3-0 flux turned on, and you will not be at a minimum. So if you're sitting somewhere on a hill for a potential, it doesn't really make sense to say I'm going to dimensionally reduce and talk about a moduli space or talk about parameter space. So I think what you've done works fine in the case it's supersymmetric, where the 3-0 component will vanish.
Well, so we have not specified the background. So it can be can have either 2,1 primitive component or 3,0 component. I agree that to start with, we need to satisfy the 10D equations of motion. So we need to have a background, and then we fluctuation. So my comment would be, as long as you can find a background which is SUSY or super non-SUSY, even if not in these compactification, maybe non-Calabi-Yau ones, at least our technology should work. Like given a background, then we should just take fluctuations and deal with the equations of motion. So at a fast pace, we need to have these background. So we have added comments like to like distinguish the non-sushi parts throughout now in our new version throughout. Like if you like to switch the non-sushi part off, then the other part would work. So we have kept this in mind now in a new version. That's would be my comment here.
Okay, yeah, that sounds good. I mean, I hope the point I'm making is clear. It's not sufficient to study the 10D two derivative equations of motion, right? Because there are no compact solutions of any kind, SUSY or non-SUSY, with flux because of the old no-go theorems of Gary Gibbons, etc. So you have to have at least the next order included, and and you have to solve those equations of motion. And that's the starting point. And then you fluctuate around it and see what kind of effective theory you get, which will work which should work
that I agree. Yeah, but as far as I see the GKP compactifications, I'm not like somehow unable to get like the GKP paper has a solution and G3 is a input, like and we get a
right.
equation for
I
work
understand.
factor. But what's
the
the
reason
problem?
the reason is the GKP paper is wrong. So they simply misunderstood how to solve the equations of motion, and they were rewriting to some extent equations of motion that we'd studied already. But if you study them correctly, including the correct ingredients to evade the no-go theorem, you will find that the Kähler potential is never no scale. And you can never truncate to assume it's no scale. That's the fundamental error in their paper. When you correct that error, you'll find that there is no potential in the case that's supersymmetric, but you will always get a potential in the case that is SUSY breaking. That's the mistake that they make. So their paper is actually incorrect. That's actually the fundamental problem.
The contributions you are saying are higher order in alpha prime, right? Like
no. You see, it's a mistake of saying if I evade these things are higher order. This is the same mistake GKP made. If you just say they're higher order in alpha prime, let me forget them. You can do that, but then you have no solution because you have no means of evading the no-go theorem. If you say I have to include them to get a solution to start with to evade the no-go theorem, then you cannot say I'm going to forget them in the effective action. So you don't get to sort of include the coupling with the purpose of evading the no-go theorem and then not include it in the dimensional reduction. You have to consistently take both into account. So you say, I will evade the no-go theorem by including a higher derivative coupling. In this case, 4 derivatives, or in M theory, 8 derivatives. I need to include it to evade the no-go theorem, but then I must also include it when I do my dimensional reduction. I cannot truncate and say, oh, I will pretend it doesn't count for the purpose of actually computing the effective action. And when you do that, then you find that it's never a no-scale potential.
Sorry, sir, I don't understand this. I'm totally confused now. If I take,
I'll explain it this way. Suppose you have a coupling.
Wait. Let me ask. Please let me ask a question. Okay.
Yeah.
So he's considering purely type 2B orientifolds. There's no D7 branes or 7 planes. Okay. Let's take only O3 and only flux. I don't see why you need any higher order of prime corrections in this simple setting. It seems to me that GKP is fully consistent at leading order for CGP.
No. It's again not consistent. So whether you consider O3 or O7, or you have to have some additional ingredient to evade the no-go theorem. It doesn't matter. There's no way to evade it without some kind of higher derivative interaction.
O3 is negative tension. That's sufficient.
But O3 plane supports couplings that you have to take into account also. So if you look if you say I'm going to restrict just to the O3 case and try to analyze that, you can also analyze that case from an M theory perspective. It's not conceptually any different. It's exactly the same as the O7 issue. So you will always have extra couplings you must account for. There's no magic in the story. I think if you actually compute in string theory the Kähler potential with the O3s, you will find that it's never no scale.
Okay,
that's the upshot.
Fine. I see what you say, but I don't agree. But I want to ask Ratul a much simpler question. Okay, I want to ask you, what is your progress compared to Martucci concerning Kähler moduli? If I just look at Kähler moduli,
I should have said that this matches with the Martucci's. Yeah. That's a complete match. Yeah.
Sorry?
So it matches with Martucci's result.
So concerning Kähler moduli, you agree, you say Martucci's analysis is okay. But
Yes, yes.
that's for complex structure. I think generically, especially if you're in non-SUSY case, there will be no completely flat complex structure directions. So then I see that you basically only do Kähler moduli, right?
Okay, so for the non-SUSY case, for the complex structure moduli, sometimes a real part of that can be axionic, like of the it is like to satisfy our linearized equation of motion. We have seen that it is possible that with non-SUSY contributions from G3, a combination of I mean, say the real part of the complex structure moduli is still flat. So for those, we need to have a metric, like moduli space metric.
You mean you disregard the exponential terms in the periods? Is that what you do? I mean, the Kähler potential and the periods have exponential terms. I mean, exponential in e to the I z or something like that, or e to the z. I mean, they also, if you switch on flux, these terms will generically also stabilize the complex structure axion type fields, right? Or you disregard.
Well, but it sometimes can keep say real part. Well, if it is all, there can be cases like all the complex structures are stabilized. Then only we have to deal with the Kähler moduli. But if there can be cases that the real part or the imaginary part of the complex, instead of a complex flat direction, we have a real flat direction, like maybe your winding of lift paper, like a real part.
So if you disregard exponential terms, basically, that's what we do there, right? We say the exponential terms are small. You're being at large complex structure, you can of course do that. Or maybe you assume that some specific Gopo-Kumar-Waffer invariants are vanishing.
We don't need to take into consideration your like the non-perturbative corrections for that. I can probably, if we have time, I can probably share. Just 1 minute.
I'm just asking which approximations you make or which assumptions you make such that you have flat directions in the complex structure moduli, which I think is not trivial.
Yes, like at least in our okay. So I'm just sharing.
So we have 2 minutes left. We're running out of time.
Okay.
So we could continue the discussion after the talk. So you could probably conclude and then continue.
Yeah, maybe then. Yeah.
Or answer to Arthur's question, and then we can continue after the talk. Okay.
Okay. Thanks for yeah. So for example, like in a old paper, like where we discussed at the level of superpotential, if there are some like relations among the derivatives of superpotential, it is possible from counting that if we want to solve the F flatness conditions, it's possible that one part, if the fluxes are related by this, it is possible that there is a like real flat directions which is from the complex structure sector. For example, in this case, probably the real part which remains flat, and this does not require the non-perturbative correction. So this has been discussed in our old paper, like in 2022. Okay. Thanks.